Welcome to Unit 2, Solving Systems of Equations. We spent a lot of time in Unit 1 looking at quadratic equations and how to solve quadratic equations. And we looked at some of the key features of a quadratic graph, which is in the shape of a parabola. In Unit 2, we're going to spend a lot of time with linear systems and look at how to solve linear systems. Today's lesson does focus on both linear and quadratics. And what we're going to look at is how to predict the number of solutions that you can get in a linear system or in a quadratic system. So first of all, what is a system of equations? A system of equations is a set of equations that you deal with all at once. And typically in a system of equations, you will have two given equations. If you are asked to solve a system of equations, that refers to you figuring out or finding out the point of intersection of the equations. So you want to know, where do these equations intersect? In grade 9, we looked at how to graph linear equations, and when we graphed, we were able to identify where the two lines intersected. A linear system refers to a set or a pair of linear equations. So in this first part, we are going to focus on predicting the number of solutions in a linear system. So we're not actually going to solve for where the two lines are intersecting. We're going to leave that for the next two lessons. But today what we're just going to do is predict how many points of intersections a linear system can have. Okay, so if we're looking to predict the number of solutions in a linear system, there are three different ways in which lines can intersect. So let's look at this first system here. We've got two lines plotted onto the grid, one in blue, one in red. I'm going to number these. So I'm going to say this is number 1 and this is number 2. So I also have the equations in the second column that matches up to those two lines. So the first equation, y equals 2x plus 1, that is the equation that matches line number 2. And the second equation, y equals negative 2x minus 3, that matches line number 1, or the blue line. So if we look at the graph, we can very clearly see that these two lines intersect, and they happen to intersect at this point right over here. And because we have a graph that's labeled with a scale, we know that the point of intersection happens to be at -1 and -1. So when you have a graph and the lines are plotted onto your graph, it's really easy to visually predict where the point of intersection is going to be. However, as you know, that's not always going to be the case, and you're not always going to have a graph handy in front of you to figure out the point of intersection. So then the only thing that we can rely on are the two given equations. So before we talk about the conditions that allow us to figure out the number of solutions, let's just review what we know about the equation of a line. So the equation of a line, as you recall, is always supposed to be in the format of y equals mx plus b. So what I know about my lines is that the number that is in front of the x, that is going to be representative of my slope. So in this first equation that I've numbered as equation number 2, my slope is 2. And in this bottom equation, my slope is -2. So I'm just going to write that. Slope is the number in front of the x, and in algebra, we use lowercase letter m to represent our slope. All right, the second number that we see in our equations, which I'm going to circle in blue, these numbers represent our y-intercept. And a y-intercept can be positive or negative, and in algebra, we use a lowercase letter b to represent our y-intercept. So when we looked at our graph, we could clearly identify that this system of equations had one point of intersection, and that one point of intersection was located at -1 and -1. Okay, but like I said before, you're not always going to be given a graph to look at to figure out where the lines intersect. So let's instead compare our two equations. And when I say compare the two equations, what we're really going to be focusing on is the slope. So the slope from the first equation and the slope from the second equation. So what I notice is that the slope in one of the lines is a positive 2. The slope in the second line is a negative 2. So those are two completely different values. So I'm going to put that in my condition box. If two lines are going to intersect and have one point of intersection, then I know that the slope of one line cannot be equal to the slope of the second line. If I were to compare my y-intercepts, one equation has a y-intercept of positive 1. The second equation has a slope of negative 3. So again, I also know that my intercepts happen to not be the same. Intercepts, it's not really important if they are the same or if they're different. What we actually care about the most is the value of the slopes. So if your lines or if your system of lines are going to have one point of intersection, then we specifically care about the slope. And the condition that needs to be fulfilled here is that your slopes cannot be the same. Okay. However, with the y-intercepts, they could be the same, they could be different. That doesn't really matter. We care more so about the slope. Okay, let's take a look at our second situation. So again, I've got two lines plotted here on the grid, one in red, one in blue. So my red line, I'm going to label this as number 1. And that actually matches up to this first equation here, y equals 2x plus 1. The blue line, I'm going to number it as number 2. And that line matches up to my second equation, y equals 2x minus 4. So when I visually look at my graph, do these two lines intersect? Actually, they don't. They do not touch each other at all. And in math, we say that these two lines are parallel. They are parallel to each other. They're running in the same direction. They will never intersect or cross each other. So I know by looking at the picture that these two equations in this particular system, they will not have any solutions. They will have no points of intersection. Okay, but again, we're not always going to have the graph to help us, so we actually need to look at the equations to help us figure out what the condition is for having no points of intersection. So again, we're going to look at the slope in each equation. So in equation number 1, my m value is a 2. And in equation number 2, my slope or my m value, oh well, it's also a 2. So that is the condition that we're looking for to have 0 solutions. So I'm going to just zoom out a little bit here. So we have no solutions. Okay, there's no points of intersection. You can say no point of intersection. And the condition is that the slope in your first equation has to be equal to the slope in your second equation. So your slopes are the same. If we go back and look at our y-intercepts, is there anything remarkable to note about them? Well, in the first equation, the y-intercept is a positive 1. And in the second equation, the y-intercept is a negative 4. So they actually happen to be different. So I'm just going to record that here in this box. So the intercept in my first equation is not the same as the intercept in the second equation. Okay, let's look at the third possible scenario that we could have. So in the picture here, I only have one line that is plotted onto the grid, but I do have two equations. So only one line, but we know that in a system of equations, there is always two lines or two equations. So let's go ahead and take a look at the equations that match this graph. And if you look at the equations, anything you notice? They're actually exactly the same. So the first equation is y equals 2x plus 1, and the second equation is also y equals 2x plus 1. So if I plot my first equation, y equals 2x plus 1 onto my grid, that's represented by this blue line here. But then the second equation is exactly the same. So if I were to plot equation number 2 onto the same grid, it's just going to overlap directly on top of the blue line that's already there. So I actually have plotted both of these equations, but they're identical to each other. So it's only going to show up as one line. So because the two lines are overlapping each other, in this particular situation, we can say that there is an infinite number of solutions. There are so many points of intersection in this particular system because the lines are lying directly on top of each other. They intersect and have the same data points on their lines. So what are the conditions for this situation? Well, if we look at our equations and we compare slopes and y-intercepts, we're obviously going to see that the slope in equation 1 is the exact same as the slope in equation 2. So these ones both have a slope of 2. And the y-intercepts are also going to be exactly the same. They are both a positive 1. So in our conditions box, if you want to have an infinite number of solutions, your slope in your first equation is going to be equal to the slope in the second equation, and the intercept in the first equation is going to be equal to the intercept in the second equation. So everything about the equations has to be identical. The slope has to be identical. The y-intercept has to be identical. Okay, so now what we're going to do is we're going to actually work on some examples. So you are not given any graphs for any of these systems of equations. You're just given the equations. And knowing now what we know about how to compare slopes and intercepts, we are going to determine the number of solutions to each linear system. So in question A, I've got two equations, 2x plus y equals 4 and x plus 3y equals 7. The first thing you want to do is number your equations. So let's call this equation number 1, the 2x plus y equals 4. And let's call this equation number 2, x plus 3y equals 7. The second thing you want to do is make sure that each of your equations is in correct linear format. Remember, we said a linear equation always has to be in the format y equals mx plus b. So just by glancing at these equations that are given to us, I can see right away that they are not in the correct format. So it's going to take us to do a little bit of rearranging and isolating to make sure that we put them into the proper format. Once they're in the proper format, then we can go ahead and look at the slopes and the y-intercepts and check all of our conditions. So I'm going to start with equation number 1. I'm going to recopy it out just so you can see it a little bit better. So it's 2x plus y equals 4. So I know that if an equation has to be in y equals mx plus b, I need to take this 2x and I need to move it over to the right-hand side. So if I move the 2x over, it's going to become a negative 2x. So here is my first equation. I'm going to do the exact same thing with equation number 2. So I'm going to just start by recopying it for you. It is x plus 3y equals 7. So same thing, I notice my x is on the wrong side. I need to bring that over. So I'm going to keep the 3y where it is. If I bring a positive x over to the right-hand side, it's going to become negative x. 7 is still there. Okay, the last thing I also need to do is I need to get rid of the 3 that is in front of the y. So I'm going to divide all of the terms in my equation by 3. So the 3's here are going to cancel out. That's going to leave me with y. Okay, remember in math, if you don't see a 1, there is like an imaginary 1 here. So I'm just going to rewrite my fraction. I can't reduce negative 1 over 3 into any kind of lower term, so I'm just going to keep it as a negative 1 over 3. Still have my x. And 7 over 3 cannot be reduced, so I'm going to keep it as 7 over 3. So here is my second equation. Now that both of my equations are in the correct format, I can go ahead and start comparing the slopes of both equations. And if we need to, we can also take a look at the y-intercepts. But remember, the slope is kind of like the key factor here. So let's start with the slope in the first equation. The slope in my first equation is this negative 2 here. And the slope in my second equation is negative 1 over 3. So are these two slopes the same? No, they are not. They're very clearly different. So I'm going to scroll down here, and I'm going to tell myself that the slope in, oops, sorry. Let's fix that up. So the slope in equation number 1 is not equal to the slope in equation number 2. So automatically that matches what we know about our first situation. When the slopes are not the same, that tells you that there is going to be one solution or one point of intersection. Okay, so let's take a look at question B. So we've got two equations. The first thing we want to do is number them. So I'm going to call this equation number 1, and I'm going to call this one equation number 2. Second thing we want to do is make sure are the equations in proper format, y equals mx plus b, and they are both not. So we're going to do the exact same thing that we did in the previous question. We need to rearrange them. So I'm going to recopy the first one, 3x plus 4y equals 14. Okay, so this 3x needs to move over. That's going to leave me with 4y equals negative 3x plus 14. Okay, there is a number in front of the y, which cannot be there, so we're going to divide everything in the equation by 4. Okay, these 4's are going to cancel out. That's going to leave me with y. And then anything that cannot be divided out nicely, we're going to leave as fractions that are reduced in lowest terms. So negative 3 over 4 does not reduce, so we're going to keep it as negative 3 over 4x plus, and 14 over 4, that can be reduced. I can divide both of those numbers by 2, which is going to give me 7 over 2. Okay, remember that you can always put fractions into your calculator, and your calculator will reduce it for you. So here is my equation for line number 1. We're going to do the same thing for number 2. So I'm going to start by rewriting it. So we've got 36 minus 12y equals 9x. So same thing, this 36 needs to move over to the right-hand side. So that's going to leave me with negative 12y equals 9x minus 36. I'm going to divide all of my terms by negative 12. So the negative 12's will cancel out. That's going to leave me with y. 9 over negative 12, that is going to reduce to negative 3 over 4. We still have the x. And negative 36 divided by negative 12, that's going to divide nice and evenly. Okay, I know two negatives will make a positive, and 36 divided by 12 is 3. So here is my second equation. So same like we did before, we're going to now compare our two equations. So I'm going to start with comparing the slope. So the slope in equation number 1 is negative 3 over 4. And the slope in equation number 2, well, it's also negative 3 over 4. So I'm going to write that down. So the slope in equation number 1 is equal to the slope in equation number 2. Okay, so if the slopes are equal, well, then there's two possibilities. We could have a system of equations that has no solutions or zero solutions, or we could have a system of equations that has an infinite number of solutions. What's going to help us decide which case it is has to do with the y-intercepts. Okay, if the slopes are the same and the intercepts are the same, well, that means that we should have gotten the exact same equation. Okay, if the intercepts are different, then that tells us that the lines are most likely just going to be parallel and they are going to have zero solutions. So let's go back and let's compare our intercepts. So in the first equation, our intercept or y-intercept was 7 over 2. And in the second equation, our intercept was a 3. So they are, in fact, different from each other. So I'm going to say my y-intercept in equation 1 is not equal to the y-intercept in equation 2. So that tells me, therefore, there are no solutions. There is no point of intersection for these two equations because the lines are parallel. They have the same slope, but different y-intercepts. That tells me the lines are parallel to each other and they will never cross each other or intersect with each other in any kind of way, so there will be no solution or no point of intersection. Okay, last question in this example. So two equations, again, we're going to start by numbering them off, number 1 and number 2. So if I look at equation number 1, it's set up perfectly. It is in the correct format, y equals mx plus b. So there's nothing that I have to do with it. I'm just going to recopy it a little bit larger for us. It doesn't need to be rearranged. It's perfect. Equation number 2, however, does need a little bit of work. So it's negative 35x plus 5y equals 15. So this negative 35x needs to move over to the right-hand side. So that's going to leave me with 5y equals 35x plus 15. Okay, I need to get rid of this 5, so I'm going to divide everything by 5. Okay, these 5s are going to cancel out. That's going to leave me with y equals 35 divided by 5, that is 7x, plus 15 divided by 5 is 3. So here's my equation. Okay, next step, we're just going to go back and compare the slopes and the intercepts in each equation. So the slope in equation number 1 is 7, and the slope in equation number 2 is also 7. So I'm going to write down that the slope in number 1 is equal to the slope in equation number 2. Okay, what about my intercepts? Well, they actually are also exactly the same. The y-intercept in the first equation is positive 3. The y-intercept in the second equation is also positive 3. So obviously, we can tell by looking, these are the exact same equation. So even though we had to rearrange number 2, it is actually the exact same equation as equation number 1. So because the slopes and the intercepts are equal and they are the exact same equation, we can say that therefore there is going to be an infinite number of solutions. Example number 2, a line is defined by the equation 3x minus 5y equals 9. Determine the equation of another line that will create a linear system with each number of solutions. So they've given us an equation of one of the lines in our system of equations. They then want you to come up with a potential second equation that would allow the system to have one solution, no solutions, or infinite solutions. So before we even worry about what the answers could possibly be, what you need to check for first is the equation that they gave you, is it in the correct format? So 3x minus 5y equals 9 is not in y equals mx plus b format. So that's the first thing that I need to do, rearrange it. So I'm going to do that here in this open bottom space. 3x minus 5y equals 9. I know that this 3x needs to move over. So I'm going to have negative 5y equals negative 3x plus 9. I need to divide every term by negative 5. Okay, the negatives and the 5s are going to cancel out. That's going to leave me with y equals. Okay, I've got negative 3 divided by negative 5. As a fraction, I know that 3/5 is not going to reduce to a smaller fraction, so I'm just going to leave it as 3 over 5x. And I also know that two negatives make a positive, so this is actually positive 3 over 5x. And then I've got 9 divided by negative 5. That's not going to reduce any further, so I'm just going to leave it as negative 9 over 5. Again, a positive and a negative makes a negative. Okay, now that our equation is in the correct format, let's go back and try to figure out what the possible answers could be. So the easiest one to start with is the infinite solutions. So if you want a system of equations that has an infinite number of solutions, well then you know that the equations have to be identical to each other. So the second equation in the system to generate something that has infinite solutions has to be identical, the exact same. So it's got to be y equals 3 over 5x minus 9 over 5. Okay, when they're the exact same, they overlap each other, and they will have infinite points of intersection. If we want something that is going to have no solution, well, in the scenario with no solution, that means that the lines are going to be parallel, which means that the slopes have to be the same. So if we look at our equation, the slope in our equation is 3 over 5. So that means that the equation that's going to go in this box also has to have a slope of 3 over 5. Now, the y-intercept could be whatever you want it to be. Okay, we know though, however, that it can't be negative 9 over 5 because then that's just going to generate the exact same equation, and that's going to give you infinite solutions. So it could be anything that you want it to be except negative 9 over 5. So I don't know, I'm just going to pick any number that I want. So I'm going to say plus 6. If I want to create a system of equations that only has one solution, well then I know based on my conditions that the slopes cannot be the same and the y-intercepts usually are also not the same. So that means you can make up any equation that you want to as long as the slope is not the same as 3 over 5 and the y-intercept should not be negative 9 over 5. So you have so many possibilities of what you could put in this box. So for example, I don't know off the top of my head, maybe I could say y equals 2x plus 5. So the slope is completely different. I picked 2. And the y-intercept is completely different. So I picked 5. Other possibilities, maybe I could say y equals x minus 3. So here the slope is 1. That's completely different. And my intercept is negative 3. That's completely different as well. Okay, so there's multiple variations of what could go into the box for one solution, because as long as the slope is different and the y-intercept is different, that is going to give you two lines that cross each other at one point of intersection. All right, so we looked at how to figure out the number of solutions in a linear system. But what if we had a quadratic system, or even a combination of a linear quadratic system? So in Unit 1, when we looked at graphing parabolas and factoring equations that were quadratic, what we learned is that you can have a parabola. So I'm just going to draw a parabola here. So you can have a parabola that intersects the x-axis at 2 spots, okay? So we found that a lot of times when we factored an equation and then I had you solve for x, you sometimes got, or majority of the times, got 2 possible different answers. But a parabola doesn't always have to have 2 points of intersection like the one that you see on your screen. It is also very possible that a parabola only has 1 point of intersection, or one solution, one spot where it touches or crosses the x-intercept or the x-axis. Or you can also have cases where your parabola does not make contact with your x-axis at all. So that means that there are 0 solutions or 0 points of intersection. So in Unit 1, we used factoring as the main way to try to solve for our values of x. However, we knew that if we couldn't factor a particular quadratic equation, then we could use the quadratic formula. So the quadratic formula is there on the top of your screen or the top of your page. X equals negative b plus or minus square root of b squared minus 4ac all divided by 2a. Now, there is a particular portion of that formula which is circled for you there, the b squared minus 4ac. Okay, that is a specific portion of the formula that we call the discriminant. The discriminant can help us determine whether or not there is a solution to a certain or specific quadratic equation. So just like what we calculated in the first example with our linear system, we said we could have one solution, no solutions, or infinite numbers of solutions. We could do the same thing for a quadratic equation or for a parabola. We can figure out if there is one solution, 2 solutions, or 0 solutions. And all of that comes from the answer that we get when we calculate the discriminant. Okay, so we're going to take a look at all 3 situations that we could get, depending on what the value of the discriminant is. So the discriminant is just that b squared minus 4ac. And just in case you've forgotten, well, what's the a, b, and c? Where's that coming from? Remember, in a quadratic equation, this is the standard form of a quadratic equation, ax squared plus bx plus c. So the number in front of the x squared, that's going to be your a value. The number that's in front of x, that's going to be your b value. And the plain number on the end, that's going to be your c value. So once you have an actual equation that you can use, you can pick out the values of a, b, and c, and you can plug them into the discriminant. So once you plug those numbers in and calculate, there's 3 different scenarios that could then arise. The first scenario is that your discriminant is going to be less than 0. So less than 0 means that you're going to get a number that is negative. If you get a number that is negative, that tells you that that particular parabola has 0 solutions. It does not intersect with the x-axis in any kind of way. So it's kind of like hovering above or below, but it doesn't actually touch the x-axis. And the reason is, if you were to get a negative number, that means that the portion underneath the square root sign in your quadratic formula or quadratic equation is going to be negative, and you can't take the square root of a negative number. So if you were to try to take the square root of a negative number and put that into your calculator, it would give you an error. So that is what signifies that there are 0 possible solutions. You can't solve that equation any further. So I'm going to write that here in this box. I'm going to say you cannot take the square root of a negative number. Okay, so let's go back and look at situation number 2. So situation number 2 is once you pick out your A, B, and C values and you plug them into the discriminant formula, and you calculate your answer, you get a number that is greater than 0. So you get a number that is a positive value. If that's a situation, then there will be 2 solutions. There will be 2 answers or 2 spots where your parabola intersects with the x-axis. And the reason is, if there's a positive number under the square root, you can take the square root and then you can have an answer that comes out to be positive. You can have an answer that comes out to be negative. You can have 2 answers that are positive. You could have 2 answers that are negative. Okay, so if there is a positive number under the square root, you will have 2 possible answers. And the last scenario is you have your A, B, and C values, you plug them into the discriminant, you calculate your answer, and your answer is 0. So you actually get 0, or that number as your answer when you calculate the discriminant. That tells you then that there will be 1 solution. So there is only 1 place where your parabola will touch or intersect with the x-axis. And the reason is, if your answer for your discriminant works out to be 0, and you try to take the square root of 0, well, the square root of 0 is just 0. There is only 1 possible number that you can get. So therefore, there is only 1 solution. So that might seem a little abstract to you, and that's okay. We're going to do 2 examples where you're going to get lots of practice with using the discriminant and making predictions about how many solutions your parabola or quadratic will have. So they have 3 different sets of linear quadratic equations here, and they want you to determine the number of solutions for each. So with the first equation, if you recall from unit number 1, okay, all of your terms have to be on the same side. And typically with a quadratic equation, we want it to be equal to 0 on the left-hand side. I mean, it could be the left-hand side, could be the right-hand side, that doesn't matter, it's whatever your preference is. But what does need to happen is that all of the terms need to be on the same side. So what I'm going to do here is I'm going to take this negative 2x squared, I'm going to bring it over to the right-hand side. And I'm going to take this negative 2 and I'm going to move that over to the right-hand side. So if I move those things over and I keep it in the proper order, I would end up with positive 2x squared plus 0.5x. I still have this minus 1, I didn't touch that. But then the negative 2 that I moved over is going to become a positive 2. So if I collect any like terms, this is going to simplify to 2x squared plus 0.5x plus 1. Okay, so here's my quadratic equation. The next thing I'm going to do is identify what is my a value, my b value, and my c value. So my a value is the number in front of x squared, so that is 2. My b value is the number in front of the x, that is 0.5. And my c value is just the plain number on the end, that is a 1. Once you have those numbers, you can then plug them into the discriminant. So the formula for your discriminant is b squared minus 4ac. It's just the portion that was underneath the square root from your quadratic formula. So I'm going to plug in all of my numbers. So my b value was 0.5 squared minus 4 multiplied by my a value, which was 2, multiplied by my c value, which was 1. Okay, so now I'm going to actually solve. So I'm going to start with 0.5 squared. So that works out to be 0.25. Okay, and then when you're doing this little portion here with the multiplication, up to you how you want to read it, but the way I like to read it is -4 multiplied by 2, that's 8. 8 multiplied by 1 is also 8. So this is going to be -8. So 0.25 minus 8 is -7.75. So that answer, we're going to check it against our 3 types of criteria that we had in the chart above. So is our answer less than 0? Is our answer greater than 0? Or is our answer 0? So my answer was -7.75. That is a number that is less than 0. So I can just make a note of that here. Okay, so I'm going to say, therefore, no, that's not how we spell no. No solution since the discriminant is less than 0. Okay, we're going to repeat the same thing with question B. So first thing we need to do is move over all of our terms onto the same side. So again, I'm just going to take my 2x and move it over to the right. And I'm going to take my -5 and move that over to the right as well. So if I move everything over to the right-hand side, that's going to leave me with 0 equals -2x squared. Okay, now it's up to you the order you want to write it in. So I have an x that is still here that I didn't touch, so I'm going to recopy that. But then I have a 2x that I moved over to the right-hand side, so that becomes -2x. I have a +3 that I didn't move, but then I have a -5 that I moved over to the right-hand side. That's going to become +5. So if I simplify and collect like terms, that leaves me with -2x squared minus x plus 8. Okay, so my next step is to identify my a, b, and c values. So this time my a value is going to be -2. My b value is going to be -1. Remember, there is a 1 here in front of the x. And my c value is +8. So those are the numbers that I'm then going to plug into the discriminant, b squared minus 4ac. So my b is -1 squared minus 4 times my a, which is -2, multiplied by my c value, which is 8. So -1 squared is +1. Okay, and then I have -4 times -2, which is -8. 8 multiplied by another 8 is +64. And 1 plus 64 is 65. So again, we're checking our answer against the three possible situations. Is my answer less than 0, greater than 0, or is my answer 0? Well, my answer is 65. 65 is greater than 0. So if I go back and look at my chart, if I have an answer that is greater than 0, I can have two possible solutions for my parabola. So I'm going to scroll back down to the bottom here, and I'm going to say, therefore, two solutions. Okay, question C, same idea. So I'm going to start by moving over this x to the right-hand side, and I'm going to move over this -3 to the right-hand side. So if I move everything over, that's going to leave me with 0 equals x squared plus 3x, take away x, take away 2, plus 3. If I simplify and collect like terms, that's going to leave me with x squared plus 2x plus 1. Okay, next step is to identify my a, b, and c values. So my a value is 1, my b value is 2, and my c value is also 1. We're going to plug those numbers into the discriminant. So b squared minus 4ac. My b value is 2, that has to be squared, minus 4 times my a value times my c value. So 2 squared is 4. Okay, -4 times 1 is -4. -4 times 1 is -4. So 4 minus 4 is 0. So again, you're going to take your answer and check it against the three different criteria or conditions. So this time my answer is exactly 0. So according to my chart up on the top of the page, if my answer is 0, that means that I'm going to just have one possible solution. So I'm going to say, therefore, one solution. Example number 2, determine the number of roots of the parabolas below. So in case you've forgotten, roots is just another way of saying find the number of solutions for each of the parabolas. So to find the number of solutions, is it going to be 0 solutions, 2 solutions, 1 solution? You just need to pick out the a, b, and c values, plug them into the discriminant, and then decide how many solutions there are going to be. So this question is nice and simple because there is nothing that you need to rearrange or reformat. All of the questions are in proper quadratic equation format. So all we're going to start by doing is pick out the a value, the b value, and the c value. So my a value for this equation is 3, my b value is 3, and my c value is -2. We're going to plug those numbers into the discriminant. So b is 3, which has to be squared, minus 4, multiplied by 3, multiplied by -2. So 3 squared is 9. Okay, -4 times 3 is -12. -12 times -2 is +24. 9 plus 24 is 33. So 33 is a number that is greater than 0. So that means that we are going to have two solutions for our parabola. Okay, so we're going to go to the last question here. Same idea. The equation is already rearranged and organized into the proper format. So we're just going to start off by identifying our A value, which is 2, our B value, which is -4, and the C value, which is -5. We're going to plug those numbers into the discriminant and see what we get. So I've got -4 squared minus 4 times 2 times -5. -4 squared is a positive 16. Please be careful throughout all of this when you are squaring numbers. Use brackets if you are trying to square a negative number. This, students always say that this is such a simple concept and it's so easy to do, and I agree, it is, but it's also very, very easy to go and make really silly mistakes and do silly stuff with the math. So please be careful with things like squaring numbers and also doing calculations with positive and negative integers. Be careful how you read which numbers are positive and which numbers are negative. Okay, so -4 squared is 16. -4 times 2 is -8. -8 multiplied by -5 is a positive 40. 60 plus 40 is 56. So again, we got an answer that is greater than 0. So that means we are going to have 2 solutions. And there you have it. So we have looked at ways to determine how many points of intersection you can have in a linear system and how many points of intersection you can have in a quadratic system. Two different methods of determining the number of solutions, but two very equal and valid ways and very quick ways of determining the number of answers you can have in each type of system.